This lecture is about solar activity and space weather, and I'm going to start off by just talking about the solar atmosphere to get us going there again. The photosphere is this region here. So I mentioned sunspots, and the sunspots can vary in size. These ones are about the size of the Earth. So they're arc minutes across, but from time to time you can get very large active regions like this one that occurred in 2001, and hopefully over the next number of years we're going to start seeing sunspots of this size again. The atmosphere and the various layers can be described by a variety of properties, their gas pressure and their magnetic pressure being two of the most important aspects of it. And you can write the ratio of these things as a term called the plasma beta. And the plasma beta tells you really how it behaves, whether it's magnetically dominated or gas pressure dominated. And in this case, the motion is dominated by gas motion, and the magnetic field kind of follows around. Now, the magnetic fields are going to be very important for space weather and also for solar radio astronomy, as you shall see. But we don't know very much about the magnetic field once you move up into the corona, because we don't measure it very well. In the photosphere, though, we can measure it with Zeeman splitting of lines. So here is a sunspot with the umbra and the penumbra, and you can see the granulation there in the background. And with an optical telescope, you can place a slit across this and then look at the Zeeman effect. What you can see is in the quiet region here, there's very little Zeeman splitting of the lines. But as you move in through the penumbra and closer to the umbra, you can see that the magnitude of the splitting of these spectral lines gets larger and larger. And so that magnitude is directly related to the magnetic field. You can also use the polarization, and it'll actually not only get you the strength of the magnetic field or the magnitude of the magnetic field, it'll get you BX, BY, and BZ. And then you can make beautiful images like this. This is a movie actually taken over a couple of days. Well, actually it's a 24-hour image taken on July the 5th from a spacecraft called Solar Dynamics Observatory. And this is the HMI instrument. But it shows you all of these small scale magnetic features. And then this is where all the kind of pops and bangs of coronal mass ejections and solar flares take place. And they're the things that will generate much radio emission from the dynamic sun, and they're the most space weather relevant of the phenomena that we will be looking at. Now, once you get up into the atmosphere, things become challenging. It's difficult to measure the magnetic field, and so modeling really plays an important role. And in order to model it, you use a set of equations called Magnetohydrodynamics. Now, these are a bit scary looking the first time you see them. Here they are in all their beauty. The MHD equations, in essence, bring together Maxwell's equations and some fluid equations and the gas law. That's really what they do. In their full complete state, they look like this, and they are rarely solved in their full complete state. Usually approximations are made in order to try and solve the equations, but also to give you something on a time scale that's reasonable. The equations in more detail, there's the mass continuity equation. There is the equation of motion. This is just F equals ma on the left-hand side of this equation. Pressure gradient, J cross B force, and gravity. This is the energy equation. So it really tells you about the temporal rate of change of gas pressure and density as well, and how they relate to any energy inputs that there are. There's also an induction equation. So this is how you make magnetic fields and remove magnetic fields through motion and diffusion. And then there's Ohm's law, and Ohm's law really in this context is interesting because it really takes the motion, the dynamics, and couples it to the magnetic field and the electric field and gives you a current. So in many cases we let J equals to zero, and we look at current-free situations. You can then solve the gas law. There is a number of ways of dealing with your equation of state. Just given an ideal gas law here. And then there's Ampere's law as well, which it relates curl B to the current. And then finally, div B equals 0, the solenoidal condition. And all of these equations are really our greatest handle at understanding the magnetic field. And a lot of the solar radio phenomena that we'll be looking at play out in the magnetic field of the corona. So these equations are quite important, and for those starting in the field, it's important to become familiar with these, maybe not to be able to solve them all, but to be comfortable with understanding how modelers are using them in order to make predictions for what the observers will then see. A very useful pack for doing this is, and this is a great simplification of the MHD equations, is called a potential field extrapolation. This is from a package by Mark DeRosa. You can go to this web page here at Lockheed Martin, and you can run the codes yourself online, or within SunPy, you can also run PFSS as well and get these models. But what they do is they'll show you an overall dipolar view of the solar atmosphere out to about 2.5 our sun, but also you can zoom in on active regions and try and understand the topology. Now, what is missing with these is that there's current missing in this. So you've no twist in the magnetic field, so it's impossible to get an eruption out of a PFSS. But if you do have a CME, say, moving through this, you may be able to look at how the CME shock moves through this and how the shock relates to the magnetic fields. Also, if you're looking at, say, type 3 radio emission, which I'll talk about in a second, they need to travel along open magnetic field lines. So these PFSS models can be useful for looking at the propagation of electrons along open magnetic field lines. So I didn't mention that, there's no twist on these, so you can't get an eruption. If you do want to get an eruption, you have to do more complicated modeling. This is a paper from Zhang et al. In Nature Communications earlier this year. But what they did is they zoomed in on an active region here that produced an eruption, and then did a 3D calculation using much more than the PFSS, and you can read about all the details in this Nature Communications paper. But what they're able to do is model the structure of the sunspot group, look at the twist in the magnetic field, the formation of a flux rope in this case, which is a wound up magnetic field line, and then look at it going unstable. And so it goes unstable by motion in the photosphere, which I mentioned earlier, causing twisting in this flux tube, and then that going unstable. And this is the kind of simulation that you can see. Now, in this case here, you begin to see this kind of dome-shaped topology of the magnetic field moving upwards as this flux rope becomes unstable, and it erupts. And it's this that then moves outwards to form shocks, to accelerate particles, and even to produce post-eruption arcades that can produce gigahertz radio waves. But these eruptions are the things that accelerate our particles and generate the shocks and produce the radio waves that we see with LOFAR and with other instruments such as I-LOFAR and so on. Now, all of this is happening low down in the solar atmosphere. It's rooted in the photosphere. But as you move up through the photosphere and in through the transition region, as I mentioned, you move up into the corona. Now, a few things are happening here. Number one, as I mentioned already, the temperature is rising dramatically from 10 to the 5 in the chromosphere, where acoustic waves are heating the chromosphere. But once you go on up here through the transition region, the temperature jumps to a megakelvin. But also the density of the gas is dropping dramatically through the transition region and out into the corona. Now, this is important in terms of trying to understand coronal shocks and coronal phenomenology, coronal radio phenomena, because this density plays a big role. Now, this is the mass density, but the electron density is what we're particularly interested in. And once you move out into this region, you're out into the corona. And this is what the corona looks like. The crown is where the word comes from, but it's highly dynamic. There are sunspots, which are the ones that your eyes are drawn to. But on smaller scales, there are small bright points going on, which presumably play a role in heating. In terms of their radio emission, there are a number of mechanisms that are important. There's free emission, there's plasma emission, there's gyro resonance or cyclotron emission, and then at the most energetic, there's gyrosynchrotron or synchrotron emission as well. And then you can also have varieties such as ECM, electron cyclotron maser emission. And later talks will by Diana Morrison and Owen Carley will talk about some of those in a little bit more detail. But we're interested in this kind of background corona and how it relates to the eruptions that we see. In order to do that, we can use measurements to work out electron densities and so on, but we can also do some modeling. Now, at its simplest, we can assume that the corona is in hydrostatic equilibrium and write down that the run of pressure as a function of height in hydrostatic equilibrium equals to the acceleration to gravity times the density. And this is the mass density. So this is density times, say, the number of electrons or the number of protons times the mass of the proton. And then you can use your equation of state where the pressure is nkt, and you get this equation here. And then integrating that, you can work out that the density, the mass density, drops off as this exponential. It does okay. You can convert this into electron densities, but this is a really important aspect of trying to understand solar radio phenomena. In this case here, we have here's a variety of different both measurements and models. Here's the surface of the sun. Here's 5 solar radii. The electron densities in an active region will be about 10 to the 9 electrons per centimeter cubed. And this model here, which is commonly used, is called the Newkirk model. And you can see the way it drops off here, almost exponential looking. And then there are other formulas. There's other equations that you'll see. The Baum-Allen formula is this dashed line here. You can see it's more, it has a more rapid drop off, but they tend to cut the same values further on out. This is a Saito model here, which starts at lower and again falls. And you can parameterize these by power laws, so r to the minus some exponent, or you can make measurements as well. So in this case, some of the models can use either a hybrid approach using measurements or fits to measurements, or else purely theoretical, like the one I saw previously. Now, the hydrostatic equilibrium doesn't work very well, but you will see it used from time to time. On the right-hand side of this plot, though, once you go further on out, and this kind of pertains to the interplanetary, the IPS work that Richard Fallows will talk about, but electron densities continue to drop as you move out. This is a lovely plot. It shows the surface of the sun here and 1 astronomical unit over here. So 1 astronomical unit is about 215 solar radii. And you can use polarization brightness measurements with a coronagraph or during eclipse to work out electron density profiles, and they continue to fall off in this form here, which you can fit and then parameterize. And there are many favorite models, but you should be careful in your choice of density model because it does affect what you infer about the physics of what's going on. Now, we did some work on this with Pietro Zucca a number of years ago during his PhD. And what we were able to do is have a hybrid approach, use LASCO coronagraph images, which Shane will talk about, plus also lower down, you can use filter ratios from AIA to work out electron densities in the lower corona. And then between the two, you can use a theoretical model to fill in the blanks. And this was one of the maps that Pietro Zucca created. And what it allows you to do is to then look at, say, if we've got a CME moving through this quadrant or this quadrant or this quadrant, you can work out what the electron densities are as you move through. Now, also in this work, it was interesting because we could use the PFSS model to then extrapolate the magnetic field from the photosphere right up into the corona and look at the structure of the magnetic field. So you have both the active region, you have both the electron densities and the magnetic fields. And then as you see, say, a type 3 radio burst or a type 2 radio burst being generated, you can try and work out where they happen. And we've also done some work on things like S bursts, which are which preferentially occur in these more higher magnetic field regions. So these maps can be useful for interpreting your data, and you can have a look at that Zuka model and recreate them for yourself using some of the software that we have made available. Now, from the corona outwards, then it expands, and it expands to form a solar wind, which was, first predicted by Parker. Now, just to show you roughly what the equations look like, we showed you the equation for hydrostatic equilibrium earlier on, and here we include gravity, the acceleration due to gravity more explicitly. But if you include expansion, then this is the expansion bit here. This is gas pressure and gravity holding it in, and this is really the motion. But with a couple of pages of mathematical manipulations, not too hard, you can show that there's a solution to this. And this was what Parker came up with in the 1950s to predict the velocity of the solar wind and how it depended on this constant and some critical velocities and critical radii. And this is the kind of solution that he found. This is the velocity as a function of distance from the sun. So this is going from the sun surface on out. But there are multiple solutions. Some of them are unphysical immediately. This doesn't connect to the surface. With these so-called type 3 solutions. This one here is double valued. This one here is double valued. But there's two solutions here that are well behaved, this so-called type 5 and type 4 solutions, which are called the solar breeze and the solar wind solution. The nice thing about this solar wind solution, these winds gradually accelerates away and asymptotically reaches a constant value, which is what is important for IPS later on. It's also temperature dependent, depending on how hot the corona is or how hot your portion of the corona is. It affects the terminal velocity that you get. So for a cooler corona, say 0.5 megakelvin to 2.5 megakelvin, you get quite a difference in the terminal velocity of the expansion of the solar wind. And that's important for those of you who have an interest in stars or sun-like stars, where the coronae of those stars may be higher. So there would be higher temperatures and hence higher solar wind or stellar wind velocities. Now, this wind whips through the heliosphere. These are some spectacular images taken by the Stereo A spacecraft. On the right-hand side is the corona, and as you can see, it has this dipolar shape guiding the solar wind into the ecliptic plane, and then through the ecliptic plane on past Jupiter. That's not Jupiter, that's Venus, and on out to the Earth. And near the Earth, then you can have L1 measurements with the ACE spacecraft or SOHO, and you can look at the solar wind density and temperature. And Richard Farrell's work, of course, will look at these transients and look at the effects that they have on pulsar signals as you move through. Or as the signals move, as the radio signals move through this solar wind. And the IPS measurements not only give you densities, but they'll also give velocities of this. And if you take multiple pulsars at different locations, you can track the evolution of velocity for these features. So that multi-wavelength actually approaches can be very useful. And these are just, I could watch these all day, I'm afraid. The structure of the solar wind changes during the cycle. It can vary from this is a quiet portion here. This is the in the late 90s. And this is from the Ulysses spacecraft that completed an orbit. Now, just be careful with this. But the passage here is along the equator and then along the poles. And what you can see is the solar wind velocity jumps up to 700-800 kilometers per second coming from the coronal holes. But then down at the equator, the velocities are down at several hundred kilometers per second, maybe 300-400 kilometers a second. As you move into solar maximum, it becomes a complete mess. You've got coronal holes all over the place, and the solar wind velocity on average is higher than you would see during solar minimum, and much less dipolar in nature. Now, the solar cycle also produces changes, and we're luckily emerging from solar minimum here, but as you emerge from solar minimum, we begin to get more sunspots, we begin to get more flares, we begin to get more solar mass ejections. And this movie really captures one of the most spectacular eruptions that we saw in recent years, in 2017. But it shows a SUV image. These are GOES X-ray images, well, X-ray ultraviolet images, and they show an eruption. They also show a shock wave or a wave and a CME moving away from the eruption. But you'll also see in the corona here a what's so-called kind of EUV wave, it's called, that moves through the atmosphere at the Alfvén speed, or well, it's not really the Alfvén speed, it's the magnetoacoustic velocity. But there's also interesting features in here. There's a post-eruption arcade. Here it goes again. Boom, filament eruption. There's a what is light glowing from along where the current sheet is thought to be. Very small spatial scales. But once these eruptions move outwards, these are a sequence of images taken from LASCO. You'll see the bubble of the corona of the CME expanding out into the solar, out into the corona. So there's hard X-rays. You'll see radio waves from them associated with them at gigahertz. You'll see a radio shock being formed as the CME moves outwards. You'll see particles being accelerated, which also will have an associated radio emission. Now, in order to understand that and the radio emission, it's important to have theoretical models, and we do these with the equations of MHD that I showed you earlier. These images are taken from a paper from Balahunian and Pete Martins, but also there's a series of papers by Lynn, Forbes, and Priest that you can go and look at. But what they do is they show, you know, the idea of an arcade that becomes sheared, the formation of a flux rope. And if you look along that axis, you see something like this. And as you kind of move these magnetic foot points together, this moves upwards to form, this is a flux rope, to form a current sheet below it, and you get a reconnection inflow, and then this accelerates off, and then below it you get a post-eruption arcade. Now there's lovely magnetic field lines above it where you'll get shocks formed. There's flanks where you can get shocks form as well. There's magnetic fields that may be open right up into the atmosphere that then can guide particles that then move out to form instabilities that will form radio bursts as well. And you'll get more about that, as I said, in some later lectures. I can't talk about eruptions without mentioning the CME Breakout Model. This was quite a revolutionary model. A more recent paper by Lynch et al. Well, Spiro Antiochos, I guess, was the originator of this as an AppJ paper. Oh God, when is it? 1998 or something like that. But this is a paper by Ben Lynch in 2008. But it captures the essence of what this breakout model is. You've got a quadrupolar magnetic field configuration, and then over time, this moves outwards. There's so-called breakout reconnection that happens on the top above it, and that kind of opens up the coronal magnetic field, allowing this flux rope to escape, and then the field lines snap back down to produce a post-eruption arcade, and then the CME moves off into space. Now, at radio wavelengths, the thing that this produces is possibly a shock wave along the flank or along the apex. The reconnection here at gigahertz, you can see, sorry, not reconnection, but the post-eruption arcade, you can see, you know, with E-OBSA. You may even see a CME, very, very difficult to capture. It was, there are some observations by Tim Bastian and others with the Nonce radiaheliograph that actually did capture one, and this would be a dream of LOFAR to actually directly image a CME. But they move off into interplanetary space, and there's a lot of radio phenomena associated with them. Now, before an eruption happens, the sun is still a bright radio source. Here are some images showing, these are from the Nonce radioheliograph, and they show a number of images at 164 megahertz, at 327 megahertz and at 410 megahertz. And you can see that the structure changes depending on the frequency that you're at. And here's just a Yoko X-ray image for comparison. But what you can see is that there is radio emission sitting above some of the active regions here. There's a missing radio emission in around coronal holes at these frequencies. If you go down to lower frequencies, you do begin to see emission from coronal holes. But this plot over here, you know, we could spend half an hour talking about it, but you can at your own leisure work through it. But what it shows you really is the flux density as a function of either frequency, which is what I prefer, or wavelength. But for LOFAR, we're talking about, you know, 10 megahertz to a few hundred, 240 megahertz. Our radio bursts are very bright by comparison with the quiet sun. So you can see that the quiet sun emission will jump by several orders of magnitude during a radio burst. And it can far outglow other astronomical sources such as the galactic background and many other radio sources. So astronomers aren't always very happy with these solar radio bursts, but they are extremely bright, particularly during flaring emission. Now, in order to interpret what you see here, it's important to look at the basic plasma physics of what's going on. This is a slide I took from Diana Morrison's talk. She'll be talking later on as well Owen about these. But this is a very powerful plot produced by Gary and Herford in 1989. But what it shows is the height above the surface in solar radii. So this is the surface of the sun down here, the photosphere, and this is the Earth out here at 1 astronomical unit. And if you go to high frequencies, so this is what EOBSA would see out around here, you're really dealing with gyroresonance and gyrosynchrotron emission. So gyroresonance just really is related to the magnetic field and the electrons gyrating about the magnetic field. And gyrosynchrotron is where they get near relativistic. As you move to lower frequencies, you move to higher heights in the atmosphere, and you get this free Bremsstrahlung emission then for the quiet areas. But as you move outwards then to say 100 megahertz or a few hundred megahertz, you begin to see plasma emission and Bremsstrahlung, and particularly during radio bursts, then plasma emission can be important, but also, you know, further on out in the solar wind, this plasma emission can be important. So that's an important plot that you really should study. And a couple of important equations that I will never forget, and nor should you if you're in this field, are the plasma frequency and the gyro frequency. So you should always remember that the plasma frequency is just 9,000 times the square root of the electron density. And Owen in his talk will talk in more detail about this, and also the gyro frequency as well. And what I'd like you to note is that this gives a direct relationship between a frequency that we can observe and a physical property. So from this frequency, we can get at electron density, and we can test those density models that I talked about earlier. Likewise with the B field, we can get at the B field from this. Also of importance for shocks is the sound speed and the Alfvén speed, and we can produce maps of those. And here's a nice plot that came from a paper by Diana Morrison in 2016. It shows the electron density and the magnetic field from a PFSS model, but also you can then calculate a map of plasma frequencies or electron cyclotron frequencies. You can look at the ratio of them, and that's important for looking at, say, electron cyclotron maser emission, or at looking at Alfvén speed as well, and where a shock might form. Okay, so I've mentioned these type 3s and type 2s, and it is a bit annoying at times in solar radio astronomy. There's a lot of these kind of terms, but this plot, which Diana will go into in a little bit more detail, show type 3s. These are really quickly drifting features which drift from high frequencies to low frequencies. So this is from near the surface of the sun to further out, several solar radii. So these are interesting, happening along open magnetic field lines. You've also got type 2s, which, you know, have a fundamental and a harmonic structure. They're drifting lanes, and there's a lot of fine structure in here. You can have these so-called noise storms here as well, which are you know, they're very broadband, and type 5 storms and type 4 storms and so on, which other speakers will go into. And you can relate these, though, to the theoretical models that I talked about earlier. Here's an erupting flux rope. This is a paper by Amari in 2014, but it shows an erupting, unwinding magnetic flux rope. But as it moves outwards, the formation of a shock and also the acceleration of particles due to reconnection to produce these very rapidly drifting features that you'll see in solar radio. And you'll get to plot some of these during the week. Shock waves as well, here they generate these features called type 2s. So these are type 3s, these are type 2s, and these are slowly drifting features, which the drift rate is more related to the velocity of that the shock is propagating at. Now, you can measure these with simple pieces of equipment. We've been working on these kind of things for a number of years. This is where we started, with simple Yagi antennas or log periodic and bicone antennas. And you can make these kind of measurements. And the reason I'm showing this is that these are kind of higher frequencies. These are lower frequencies. And later on, you'll be doing some tutorials where you'll be plotting these low frequencies with some intermediate frequencies and then some spacecraft measurements. But what this allows you to do is track solar radio bursts the whole way from where they originate, close to erupting arcades, the whole way out through to near the sun. So the radio observations allow you to do that. In this case here, this was a paper by Carly. He was looking at fine scale structure that he saw down here called herringbones, and they have a forward and a reverse drift feature. And then if you combine it with radio imaging, you can work out where they happen and how it relates to a shock wave as well. So you can read that paper at your own leisure. Of course, it's really important to get imaging and spectroscopy together with radio observations. This image here shows you the radio telescope called LOFAR, the ILT, or the International LOFAR Telescope. It starts in the Netherlands and stretches out to Ireland, out here to Eastern Europe, really. Hopefully someday down to somewhere around here, out to Bulgaria, and soon down to Italy as well. And we in Ireland built a LOFAR station, just to give you an idea of what someday you will have in Bulgaria, I hope. This is about like 3 football or maybe 2 football fields in size. These are the low band antennas, and the high band antennas picking up below FM radio at 10 to 90 megahertz and at 110 to 240 megahertz here, and that then all gets correlated. And you can do things like this. You can make tide array images. These are from a paper by Diana Morrison, and you'll see at the top these blobs, and we're able to track the blobs and say where they are. But at the same time, you can look at different portions of the atmosphere and see these rapidly drifting features. So the imaging spectroscopy is very powerful for these. And again, I think Aoife will talk about some interferometry and possibly Pierce as well, and maybe Kira. And also then you'll do plenty of imaging later on. Okay, here's, we talk a lot about big phenomena and CMEs and flares, but sometimes there's very little going on in the X-rays. Here's an example, the GOES X-rays, there was just nothing going on. And then Pierce Murphy took a look at this region and saw, there's actually something going on very short timescales. And then if you zoom in again, there's lots of fine structure. What LOFAR can do with its rapid time variability and its good bandwidth or frequency sensitivity, it can just show you all these fine structure. And then with LOFAR, you can make interferometric images as well. So you can not only tell where these are their drift rate, but you can tell where they are coming from and then relate them to the solar atmosphere and do, say, potential field extrapolations if you so wish. Now, from the smallest features, then we can move on to the largest features, and you'll be doing some plotting of EUV images and X-ray and EUV images and white light coronagraph images later on with Shane. But this is the kind of thing that you can do. You can look at the motion of a CME expanding out through the atmosphere. And then related, you'll be plotting these GOES light curves as well. Laura will be doing a little bit of that in the introduction to Python or to SunPy. And then you can make these dynamic spectra. But what this does is the radio data on its own is quite limited, and maybe even the optical images are quite limited as well. But combined, you can then put them together and work out where this is going, what its velocity is, where the shock wave might be, and relate it to, say, the acceleration of particles and, say, the type 2 radio emission that you can see. Now, to do that, we go back to the density models, and if you have a CME that's fast enough, you generate a shock wave, and then you can get fundamental emission and harmonic emission. And once you measure your fundamental emission, you can use a density model, that's really what that arrow represents, and you can get what electron density profile, and you can work out the height. So you can get from an observation to a physical number to a height measurement as well. I'm just going to check my time. Okay, seem to be doing all right, and I'll start winding up soon enough. Okay, here's some work that also, just to give you more of an insight, there's a lot of fine structure in these spectra, and you can do other things like looking at band splitting in these phenomena and then work out even more detailed properties of the shock, like its compression ratio and the Mach number. And you can then relate it to things like potential field models that I talked about earlier. And as this, say, CME front moves outwards, you can look at the norm or the shock norm and then relate how that, its orientation to the magnetic field lines. So here, this shock norm here is parallel to the magnetic field lines, but this one here, so this is called quasi-parallel, and then this one here is at some angle, so it might be, you know, out here that it becomes quasi-perpendicular. And once you're quasi-perpendicular, that's a very good place to accelerate particles. So the combination of the radio data with these helps us with understanding where particle acceleration may happen. Sophie Murray will talk about forecasting later on. This is another 2017 event, should I say, where a large sunspot group grew over a number of days from September 3rd to the 7th to the 10th, I'm showing here. And here's the X-rays jumping up, and then there's an X9.3 flare and an X8.2 flare. But it was the active region that produced this spectacular event that I showed earlier on. You know, as that erupted, there was this beautiful little bubble formed. So this like plasmoid shape bubble that moved outwards. But as it did, it produced a very well-defined shock in the solar atmosphere. But with I-LOFAR and with the LOFAR core, you can take high resolution. So with an international station, you can look at the dynamic spectra, and it is a complete mess. But if you zoom in with the core, you can see all kinds of drifting features. So forward and reverse drifting features here, these are called herringbones, and that can tell you about particle beams going downwards and going upwards. And later on, we'll talk about the different types of mechanisms that can produce them. Here's the zoomed in dynamic spectrum again, and also the imaging from the LOFAR core as well, and how it relates to an expanding front. And what you can see is that the radio emission, these are at, you know, in the low band antennas, wavelengths at 35 to 50 megahertz. And you can see this emission along the flank of the CME, and then these pops of bursts of particle acceleration going on and on. Okay, I'll move along quickly there. I just skipped that slide. And this is just a particularly nice figure. I think it's a bit busy, but you can read that paper by Morrison et al. In Nature Astronomy. But this is a zoom in that shows you the different frequencies and the different drifts. And then with LOFAR, if you're imaging, you can see this turquoise image here, then the green image here. I'm slightly colorblind, this is very hard. No, it should be going downwards and upwards is what these colors are. And sorry, my screen is a bit small, so I really have problems distinguishing those. And this is a 3D kind of hairy ball model that with PFSS that Owen produced. And you can look at then where open magnetic fields might be and where these herringbones are accelerated. Now, I've talked a lot about solar phenomena, and more detail will be going into that. So I hope your head isn't spinning too much, but it gives you a little bit of a flavor of some of the phenomena, and others will do a deeper dive into those. So that should give you a taste. But all of these things that I've talked about here are of importance to space weather. And we're running a project called the LOFAR for Space Weather Project. You can have a look at this website here. But really, it's about upgrading I-LOFAR, the International LOFAR Telescope, to look at phenomena that are important for things like spacecraft, electronics, or the aurora borealis, or the Earth's magnetosphere. And so the LOFAR for Space Weather is coming up with a new design to extend LOFAR so that it can monitor the sun and the ionosphere and do interplanetary measurements, IPS measurements. And that'll give you a very comprehensive view of the sun-Earth connection through the solar observations, which I've really focused on. The IPS, with Richard Fallows will talk about, and then Laura Hayes will talk about the ionospheric response as well. Now, also of importance, there is space weather on other planets. If you go out to Jupiter, it has an aurora itself. There are radiation belts. And if you look with LOFAR or low frequencies, you can see decametric emission. And Coronal will talk about that, and Katrina Jackman will also talk about that as well. But you can turn LOFAR on Jupiter and look for so-called decametric emission that comes from us. And in fact, exoplanets would also show something similar. And this plot here shows you some initial LOFAR observations and some non-say decametric emissions. And you can see familiar type of radio emissions, the physics of which Coronal and Katrina will talk about. Okay, so let me finish up here. I guess what the purpose of this talk is was to give you a real survey. There's some concepts in there that are challenging. In the lectures to come, you're going to get more information on that. I hope it's whetted your appetite. But I think ultimately it's kind of the multi-wavelength approach, with radio being a really important aspect of that gives us an insight into particle acceleration and shocks that are the drivers of space weather that we see throughout the heliosphere, from what happens in interplanetary space to their impacts on the Earth, Mars, and Jupiter. And they tell us about very fundamental things. They tell us about plasma properties. They tell us about sites of particle acceleration. They tell us about propagation. They tell us about oscillations and waves, which I didn't talk about at all. And they also have a real impact on scattering and turbulence, which others will go into greater detail about. Okay, sorry for going over for a few minutes there, and I'm happy to take any talk or any questions.
I think there's one or two in the chat, Peter, that came in earlier on.
I hope you didn't hear my cat there. My cat started howling about 3 minutes ago, looking to come into the room. All right, what's in the chat? I think I have to stop sharing to see that. Oh yeah. People want to read them out to me. Whoever has it, or shall I just read them myself?
Yeah, I can read it out, Peter, if you want.
Yeah.
There was a really great question by Mohammed, and it's one of my favorites about coronal heating. Is, does the temperature increase at the transition region due to the decrease in density to maintain constant pressure, or due to something else? In other words, why does one drop and the other go up? Are they related? And for example, is it related to electric currents in that region or something different?
Oh God, it's a great question. I did my PhD on the transition region. I spent a lot of my time looking at EUV emission. The gas pressure is basically hydrostatic, but there's the chromosphere is really heated by acoustic waves, and as they come up, they dump all of their energy in the upper chromosphere. So the shock waves form. There's some lovely papers by the Oslo group on that. Once you go into the transition region, there's no way of getting that acoustic energy in there. So there must be some kind of mechanical energy going on that's driving that. So if you look and find detail with spectra, like with Iris, you'll see non-thermal motion, mass motions, which is indicative of turbulence. You'll see reconnection, kind of jets going off. So there must be some kind of mechanical thing. You'll also see some evidence for maybe waves in there. So you can't account for it by just simple hydrodynamic observation of temperature, pressure balance. There has to be some kind of mechanical input there. And I think it's still you know, a challenging one to understand exactly, but you know, small scale brightenings and wave heating are two of the most likely ones to cause the heating of the transition region, and then going on out to create that temperature rise. But what's really hard is that it goes from, you know, 10 to the 5 to 10 to the 6, a megakelvin over a couple of hundred kilometers. You know, it's very strange, despite what I've said already with some insight into it. Great question, though.
Great. There was another one there that I answered, but it says, since the harmonic band of the type 2 radio burst is caused by the coalescence of two Langmuir waves, what governs that mechanism? What causes the coalescence? That's a really difficult question to answer all in one.
Yeah, what causes the coalescence? I'm not entirely sure what causes the coalescence of it. You know, to generate the Langmuir waves is straightforward enough. You just need a bump and tail instability on your Maxwell-Boltzmann distribution of velocities, and that'll cause the instability. But the coalescence, I'm not entirely sure. In Owen's lecture on the theory, he does talk a little bit more about that, but I'm not sure if, Owen, you're even able to say something about.
Yeah, I gave a reply there. That's called a three-wave process, or wave-wave interaction. And it's actually an active area of research, how those waves coalesce, and what determines it. And the simple answer is because there's three waves involved and the energy conservation involves, their frequencies have to match and their wave numbers have to match. And then there's also these probabilities of interactions between the waves, which is actually pretty similar between the probability of the interaction of a photon with an atom during those transitions. It operates a little bit like that. And all I say is it's kind of a very modern active area of research, and I'm not sure if the answer is actually really known, to be honest. People are working on it, I would say.
All right, do we have any more?
Awesome, yeah. I mean, unless there's any other questions, I'd like to thank Peter again. And then, so yeah, we now have a 15-minute break scheduled. And so we'll start up again at 11:30. I'm going to leave the Zoom on. And I guess I'll see everyone in 15 minutes. Time to grab a quick coffee or tea, rejuvenate for the next session.
Talk to you soon.
Thanks.
Thanks, Peter. Cheers.
Thank you, Peter.